Let's take a look at example 3.1.1. We're looking for the speed of a falling object. So in this example, we have a mass given to us with m equals 2 slugs, and this drops from a height of 30 feet above the ground. So we can see this figure given to us below in our given diagram here. They ask us to determine its speed after it drops 20 feet to a platform that is 10 feet above the ground. So we see here, here's our ground level here. Here's our platform right there. Here's our mass, m equals 2 slugs up top here. This is 20 feet above the platform. Platform height is 10 feet off the ground. So now let's create our setup page from the given information in our problem statement. In our setup page, we want a couple different things. We want to have all of the given information from the problem statement and diagram clearly labeled with our variables and our units and values. Redraw a simplified version of our given diagram and clearly write out what they're asking us to solve for. So what they give us is we know our mass is equal to 2 in units of slugs. Our initial position, x naught, is at 30 feet above the ground. Our final position is at 10 feet above the ground. Our initial velocity is 0 feet per second, and that is because it starts from rest when it's dropped. And our acceleration due to gravity is 32.2 feet per second squared. We really want to pay attention to what units we use here. We're dealing with feet with everything else here, so we want to be in feet per second squared for our acceleration due to gravity. What are they asking us to solve for? Well, they ask us to find the speed of the mass after it drops that 20 feet to a platform that's then 10 feet off the ground there. So we're looking for our v for our speed. Assumptions we want to make with this problem: we're going to assume that there's no air resistance and that the object is dropped from rest, so its initial velocity is 0. So now that we've taken the time to create our setup page, know exactly what we're given, what they're asking us to solve for, and all the assumptions we've made, we can now begin our solution. So as we begin the solution, the first thing we need to do is establish a reference plane. Now we have a couple different options here. We can do the ground as a reference plane, we could do the height of the platform as a reference plane, or we can do the starting height where the mass is released from as the reference plane right there. So those are three different options, and there's pros and cons to each one that will help either simplify or complicate the problem as we're going through the solution. So we don't really know. We can just pick one, and always a good one is the ground. So let's just say, let's start with the ground as our reference plane. Everything we measured from that reference of the ground. So every distance will be measured from ground being 0. So what this does is this gives us a starting position for the mass. So our starting position for the mass, if the mass is 20 feet above the platform and the platform is 10 feet above the ground, that means our starting position for our mass is x naught is equal to 30 feet. So it starts 30 feet above the ground, which is 20 feet above the platform, that is 10 feet above the ground. So this is where it gets a little complicated, and I know I've stated this a couple times and wrote it down as well, and it's in the diagram. You want to make sure as you're going through the solution that you can reference back and understand what each of these is labeled and where everything is referenced from. So with this all written down, understanding what our starting position is, now we want to choose our key equation for solving this problem here. So our governing equation for this problem here comes from equation 3.1.11 on page 132 of our textbook, section 3.1.1. This is assuming you're having the 4th edition of the textbook. If not, it should be in the same section. Pages might be just a little bit different. So our key equation here is going to be mv squared over 2 minus mv naught squared over 2 plus mg plus x minus x naught is equal to 0. So now that we have our governing equation, we want to think about, well, what do we know? Which of these variables do we have information for that we can plug into this? And then reduce it and simplify it down. So I can notice here, okay, I can pull out a 1/2 in front of this and an m in front of this. I pull out a 1/2 m here times my v squared minus my v naught squared, my final velocity minus my initial velocity, plus my mg times my final position minus my initial position here. And notice that there's an m on both sides, so I really can not really worry about plugging in actual values for that because those will cancel out. But everything else I know I'm going to have known values that I can start plugging in for. So that'll be the next step, is to plug into this simplified equation. So now I rewrite out on top of this page here the simplified form of our governing equation. Even though it's on our previous page, I still like to have it here because I'm also going to write out all of my known values from the problem statement and from my assumptions. That way I can look at the problem here and plug directly in all at one page and not have to keep flipping back and forth. So I have my 1/2 m times v squared minus v naught squared final velocity minus initial velocity plus the mass times acceleration due to gravity times the change in my position of my final position minus my initial position of the mass itself. Well, I know my mass m is equal to 2 slugs. I know my initial velocity v naught is equal to 0 feet per second because it starts from rest. V is my final velocity, and this is what I'm looking for, and this is the height of the mass at 10 feet above the ground. So at our final position, x is equal to 10 is what we're going to looking for our velocity there. And g is our acceleration due to gravity. Pay attention to what units we're in. We want to be at 32.2 feet per second squared. H is that platform height above the ground, where we picked our ground to be our reference plane at 0. So the height of the platform is going to be that x equals 10 again, as we mentioned up here for our final velocity. And x naught is the starting position from where the mass is released. So again, that is its distance above the ground, which is the 10 plus 20 or 30 feet for our x naught. So now, because of our reference plane, this dictates our x and our x naught, and those are what we're going to plug in up here into our governing equation. So when we plug those values in, we're going to leave our m as m because we notice those will cancel out in our previous equation there. So we have 1/2 m times v squared minus v naught squared, which is our 0 from initial velocity there, because it starts from rest, plus m times our acceleration due to gravity of 32.2, times our change in our position of x minus x naught, 10 minus 30. This is equal to 0. Rearrange, get rid of put this over on the right-hand side of our equation here. We're left with 1/2 mv squared is equal to 20m times 32.2. M and m do cancel out, so we didn't need to plug in our values for that there. So end up with 1/2 v squared is equal to 20 times 32.2. Again, pay attention to our units here. So if you guys go in through what the author did, take a look and see what they did for their example problem, for their solution here. Really important to pay attention to what units we're in here. So this is at 32.2 feet per second squared. We're not at 9.81 meters per second squared. So make sure our units check out. So that's something to mention as well. You notice I didn't write my units in here, but I do have them up in my given equation here. Doing unit analysis is very important when you're double checking your work in these problems. So it doesn't hurt to go in and leave your units through all of your values here when you start plugging in. That way you make sure your final answer, your V, isn't exactly what you think it is in feet per second. So you can do your unit analysis, cancel things out, and make sure that that comes out in feet per second. So continuing on, once we plug in the correct units for acceleration due to gravity, we can reduce this, put our 2 over on this side here, eliminate from here. So V squared is equal to 40 times 32.2. Square root of both sides, V is equal to square root of 1288, or when we do that out, velocity is equal to 35.88 feet per second. So that's our velocity when our mass reaches the height of that platform, which is 10 feet above the ground. So now that we've gone through and solved it using the ground as our reference plane, let's resolve this again just to see how it changes our solution, but not our final answer, if we set a different spot as our reference plane. So this time here, instead of the ground being the reference plane here, with x equals to 0 there, let's set our final position where we're interested in the mass ending up as our reference plane here. So our x is equal to 0 when the ball is at our platform right here. So rather than the ground being 0, our platform height is 0. So that's going to change our starting position of the mass because it's with reference to the top of this and not reference to the ground. So let's go change all of our variables here based upon this new reference. So our mass isn't going to change. Mass is still equal to m is equal to 2 units of slugs. Our starting height of the mass will change. So this is now 20 feet as compared to the previous 30 feet because our x naught is going to be 20 feet above that platform height. Our initial velocity isn't going to change. It still starts from rest. So v naught is equal to 0 feet per second. Our platform height is now going to change. Our platform height is our reference. So this is x equals 0, whereas before it was x equals 10 when we were talking about its distance off the ground. Acceleration due to gravity, still not going to change, still the same units, 32.2 feet per second squared. So as we begin our solution, with this new reference point here from the height of the platform. Still want to pick a governing equation, still going to use that same governing equation there, equation 3.1.11 on page 132 of the textbook, section 3.1.1, again, if you're using your 4th edition. And this is our governing equation listed here. mv squared over 2 minus mv naught squared over 2 plus mg times our difference in position x minus x naught, final position minus initial position, is equal to 0. Reduce and simplify, same way we did in the first part of our solution. 1/2 m times the difference in our velocities, final velocity minus initial velocities squared, plus mg times our final position minus initial position is equal to 0. Again, I like to rewrite this out in general form and then put in all of my variables, my known values here, so it makes life easy as I plug into it and it's all in one location. So I do that there. Okay, my initial velocity starts from s is 0 feet per second. Initial position, where the ball is released from, is 20 feet. Our mass is equal to 2 slugs. Acceleration due to gravity, 32.2 feet per second squared. Our final position is now at 0 when it hits the height of that platform there with our new reference, and that's in feet. And our v is what we're searching for, our final velocity when it gets to that platform height. So I can now plug those values into my governing equation there. This becomes 1/2 m. Leave the m's the same because I know they're going to cancel out, not plug in numeric values for those, times v squared minus 0, initial velocity of 0, plus m times acceleration due to gravity of 32.2 feet per second squared, times our final position minus our initial position. Final position is 0 when it reaches the platform height. Initial position is 20, where we're releasing it from. Reduce and simplify, that goes away, our 0 there. This becomes 1/2 mv squared minus 20 times the mass times 32.2 is equal to 0. So we can keep going from there. Reduce and simplify. Let's move this down a little bit so you guys can see that. So we look at this here. Well, let's have an m on both sides. It can cancel. 1/2 mv squared is equal to 20 m times 32.2. Or cancel those m's out. Solve for v. So we now have 1/2 v squared is equal to 20 times 32.2. V squared is equal to 20 times 32.2 when we move that 2 over here. Square root of both sides, v is equal to square root of 40 times 32.2, or v is equal to square root of 1,288. We do that out. Velocity is equal to 35.8 feet per second. Units do double check if we do out our unit analysis. So we can see, even though that we changed our reference plane, we did it from the height of the platform rather than the ground, we still arrive at the same answer. And you could go back for practice and change it again, and this time do our third option for our references and say that our starting position where we release the mass from, set that as x equals 0. And go from there, and then have it drop down to where the platform is there. Change all of your values, your x and your x naught, with that. Do that, prove to yourself you still get that same velocity regardless of what you choose for reference plane. It just messes with sign convention and what your values are.